And I think we can start the today's Friday seminar. Okay. Thank you very much for coming to the Friday seminar. Today we're very excited to have Michael Mead as a speaker. He did his PhD in Oxford by being supervised by Frederick Law. And then he has been doing his first postdoc project so far. So he will tell us about axion couplings and heterotic string theory today. Okay, let's go ahead.
Thanks. Yeah, thanks for the invitation. It's very nice to be here and to have the opportunity to speak. So do I have to stay close to this for the audio to work? Okay. So yeah, as Gongjun mentioned, I'm going to be talking about axion couplings in heterotic string theory in particular, and this is work done with Pratik Agrawal and Mario Reg, who's now at CERN. Pratik's now at Santa Barbara. And it's based on these two papers here. This earlier one is a similar kind of setup, where we determine the axion couplings in grand unified theories, which I'll go through. And then the second paper is a similar sort of result for the heterotic string axions coming from heterotic string theory. So yeah, I'll go quickly through the unified theory case because it's important to understand the heterotic case. But the basic result or the basic thing we want to leverage is the okay. Can you see that? Yeah, okay. So but the basic idea is like what we want to try and understand is like what could axion searches or the potential or hopeful discovery of an axion teach us about physics in sort of the far UV, so grand unit scales, which are sort of inaccessible by other means. So scales, energy scales associated with coupling unification or the string theory, the string scale. And the reason why you might actually think that axions can do this where sort of other physics cannot is that axion couplings to specifically the couplings to gauge bosons are topological quantities. They're related to anomaly coefficients, so they can be matched from the UV to the IR. So they're not affected by any sort of RG evolution or whatever degrees of freedom you add to your theory between here and say the gut or the string scale. So they're sort of a pristine carrier of the information of the UV theory in a way that other couplings and parameters are not. And so for related ideas, there's a list of papers here. So these are all somehow related to this sort of topological nature to the axion couplings to gauge bosons and the sort of different phenomenological applications. So it's in that sense, it's it's a well-studied field. And also the other thing which makes this useful is that the best limits for axions and probably the most likely way that we would see an axion in an experiment is via its coupling to photons. So this is a plot of the experimental landscape with the axion mass on the x-axis and the photon coupling on the y-axis. It's taken from Kieran's this website where it collates all these bounds. And so these solid lines are existing constraints. So the different colors are different types of experiments. And then this dotted line is the projection for future haloscopes. So I just put this here to point out first of all, the number of different experiments that are looking for axions via the photon coupling specifically, which is what we're going to focus on. And also that they're mostly sensitive to this sort of region of parameter space above the QCD axion line. And we're going to show, just sort of fast forwarding a bit, that in these unified theories and heterotic models, you don't find axions living above the QCD axion line on this plot. So if there was sort of anything you found, if one of these experiments saw something with a axion photon coupling larger than the QCD axion value, then you could say that that's not compatible with unification or the heterotic string models. Axions slightly different couplings to Mhm.
supplies one mass magnitude. So yeah, normally, obviously one part of one massive and
Yeah.
massless particle coupling to that, which would be all the way to the left.
Right.
You're saying it's not.
Yes. The reason is because that's exactly the setup basically, but in a unified theory, you have one coupling to both. So the same linear combination that gets the mass is the same one that couples to the photons. So there's only one anomaly coefficient. That's essentially the basis of all.
But what if you had a gauge? This is very setup. You just told me that.
You could have another gauge group, but that doesn't change if the standard model is unified, then the anomaly coefficients are related to the QED and QCD. Yeah.
That just supplies for you or I.
But then it would not couple to photons.
A particular form for brand.
Yeah, because it could be a mixture.
No. No. This standard model is unified is my definition of unification into a gauge group. I don't care what it is. Okay, well, let's can ask further questions later. So okay, I'm going to first quickly do a review of axions. So what I mean by an axion and what the allowed couplings are, and review the QCD axion, and then talk about axions in unified theories. And so we'll talk about the QCD axion and unified theories, and then also mixing. And then I'll talk about heterotic string models. If we have time, which I highly doubt, I've never yet had time, we'll talk about overfold guts. So, but yeah, these middle sections are sort of the main point. But okay, so let's first quickly go through axions and their coupling. So by an axion, I just mean a scalar with a discrete shift symmetry. So this is an exact symmetry, this discrete symmetry. It's 2 pi periodic. And they can arise from sort of a variety of different scenarios. In a 4D theory, they're the Goldstone bosons associated with a broken U1 symmetry. So if I have a complex scalar and it gets a VEV, the phase of that scalar is the axion. So the string setup, which is what will happen in the heterotic case, they can come from higher form fields, so like gauge fields or gauge fields with extra indices propagating on compact dimensions. So when you do go dimensionally reduced to the 4D theory, you're left with axions. And this is the generic case in string compactifications. In all the phenomenological models in string theory, you get at least some axions via this second mechanism. And then there's a number of phenomenological reasons, which I'm not really going to talk about, apart from the solving the strong CP problem. We'll be talking about the QCD axion. But they could also explain things like quintessence or dark matter. They could play a role in inflation. So there's a number of reasons why you might care about them. But I'm really going to focus on just assuming that they exist. And I'll assume there's a solution to the strong CP problem and just look at their properties in these two theories. Okay. So this shift symmetry, it governs the allowed couplings that axions can have. And you can sort of write down couplings which are manifestly shift symmetric. So this coupling to fermions is shift symmetric because it's the derivative of the axion which appears. And you can have like trigonometric functions or something like this, which is periodic, some function which is periodic in A on FA going to adding 2 pi to A on FA. And then you also have this coupling to gauge bosons, which doesn't necessarily look like it's invariant under this shift symmetry. And in general, it's not. It's only invariant under if the coupling to the gauge bosons is quantized, which is sort of an important part of the result, because that means that if you have a coupling like these two in the Lagrangian, you could add a coefficient out the front, and then that would be renormalized by other fields, whatever you have in your theory. So that could become very small or very large in the IR, depending on the model. But the integer coefficient of this coupling cannot be. It's just an integer. It stays the same. So I'm going to go through a quick argument why that should be the case. It comes from considering the theory in Euclidean space. So I have this Euclidean axion. So I've now normalized that same coupling I wrote down on the other page with the gauge coupling alpha here. And I have an axion coupled to GG tilde. And then there's some coupling constant, this curly A, which I want to determine. On an S4, this integral evaluates to an integer. And then if I can just, so if I just imagine this gauge, the G has a background which such that this integral is equal to N, then I can shift the axion by 2 pi, and I get that the action shifts by this amount. And what I need is that e to the minus s is invariant under this shift for this symmetry. So this curly A should be an integer. Yeah. Oh, like a sphere, a 4-dimensional sphere. Yeah. Yeah.
Guessing you probably might want to use T4 because S4 feels trivial. S4 is a bit big.
I wasn't necessarily. I was thinking of this as on non-abelian gauge, but okay. Right. Yeah, well, I really want to talk about guts. So, but yeah, okay. But yeah, so basically this coupling, at least in units of alpha on 8 pi, has to be an integer. Okay. Okay, so that's just to sort of set up this fact that we have integer couplings to gauge boson. And now I'm going to talk about the QCD axion. So QCD axion is the one that is an axion that solves the strong CP problem. The strong CP problem being a fine-tuning problem of the standard model. So we can write down this term in the standard model has this theta bar term. So it's like the coupling on the previous page, but without its theta bar is just a parameter, not a field. And the fact that the neutron electric dipole moment has not been observed bounds this parameter to be less than 10 to the minus 11. It's a priori, it's 2 pi periodic, but it's anyway, it's an order 1, a priori, it's an order 1 sort of angle. So the fact that it's very close to 0 is the fine-tuning problem, which we call the strong CP problem. But if I introduce an axion with a coupling, so if I call add this coupling where G is QCD, and then I'm going to say that this coupling constant is N, then I don't just have this theta bar parameter, I have also a contribution from the axion. And then so the total contribution is this theta bar plus AN over FA. And then when I can then derive the chiral Lagrangian, and I find that the potential for the axion is minimized so that this like effective theta, which is the combination of this bare parameter plus the axion, this potential is minimized such the whole thing is 0. So this solves the strong CP problem, and also has the nice feature that it's essentially a 1 parameter model, because we can derive the mass from this potential, and all of these quantities and this F pi and M pi are known just from QCD. So they're not an input to the theory. And then the mass is just given by this QCD scale over FA. And the photon coupling, which is what we want to use to look for it experimentally, is given by this ratio of E over N. So E is if I added an explicit coupling to FF joule, the photons, and N, well, the fact that N appears here is because I've gone from this capital F. So this capital F over N, I've called little f. That's just a convention, which is why this N appears here. And this minus 1.92 is from mixing with the pion. So up to this sort of rational number here, and you always have a sort of photon coupling, which in typical models is sort of an order 1 number times alpha on FA. So again, we know roughly what the axion coupling to photons is and its mass, which is why on these plots we can draw this QCD axion line. We do have this unknown rational number here, E over N, which you can sort of pick some realistic values for, which gives the width of this line here. So we have a well-defined prediction for where, within some uncertainty based on this E over N, where the QCD axion should fall on this plot. Okay, so any questions about that? Right, let's keep moving on. Okay, great. So now I'm going to talk about what happens in grand unified theory. So before, basically, this E over N, this E over N are in principle independent numbers, and we'll show that in grand unified theories they're not.
So if I have these four subsequent charges. Okay. I don't recall that. I think two such that this is really small.
I don't think I think this combination,
Yeah.
I think that usually what people consider as the maximum thing you can do is getting E on N is equal to 2, and then you get 2 orders of magnitude. You get a 0.08 here. Other than that, I think it's kind of hard to get. I mean, I forget exactly what the numbers are, like how far you can do it, but you sort of run into problems because you just need very large integers here. So you need large Pechi-Quinn charges of the whatever fermions are giving you this anomaly. So
Yeah, I think people did analysis where they had all sorts of followed back sketch, all sorts of shit. There was a cancellation.
yeah,
Just by adding.
right. But to get 2 integers to cancel 1.92, you need to start adding like very large numbers of degree of freedom. Yeah. Yeah. But I mean, to get a good cancellation, you need to like have a 2 orders of like a 0.08 here when E on N is 2 is like something reasonable, but you
See, I have big and choose up or down for Pechi-Quinn charge within the that needs to be my pick. If that's the case, I think I can see that. But it might be wrong.
yeah, I think that people have argued that it starts to become wrong from other perspectives because you either have a large number of degrees of freedom or very large PQ charges, and there's some other things which go wrong, but I don't know off the top of my head. But if you just allow the Q of the charge of the quarks to be large enough so that you can balance 2 large integers to get to cancel this irrational piece, then you can make it a small like.
It's not necessarily violent. It's a coupling to GG4 and what transpires once you kind of it's I would say it's a gross coupling of people from. So that's what it is. Now, also model the it's when the file here this way. That's all.
So like extra degrees of freedom, which
Now we'll choose the patient charges for up and down work.
but that would change the E on N.
This might be wrong for some other reasons.
But you're saying you can change the 1.92? I thought that was fixed by the Carol Lagrangian. Okay.
So strictly coupling GGU.
Mm-hmm.
If I have coupling
Okay.
precisely.
Okay. Interesting. Um. hmm. Okay. So, right. Well, for this, I'm going to take this as the result. Well, this as the result, and then ask what happens in unified theories. So here we just have one gauge group in the UV. So we have one. So I'm going to, for the setup, this, we have one. So when I say one gauge group, I just mean the standard model is unified into one gauge group. You could have a hidden sector that wouldn't change the story, as long as all the standard model gauge groups come from one. Yeah.
Something like this. What if the SU2 times U1 gets you
Yeah, I was thinking of trinification.
unification? Yeah, that's
Yeah,
what I'm thinking.
SU3Q.
Yeah. So then you would, I'll come to that. So the results work for the bound in the parameter space works when it's all unified. So if you have trinification and it's not further unified into E6,
Yeah.
then you can get axions wherever you like.
Yeah, that's what I meant before.
Yeah. Oh, okay.
It's also
That's
Okay.
too.
Right.
the thing that we generally would probably want is to get rid of the Landau folder. But why everybody else should be unified is a bit more, based on your spirituality. So
I have a very strict spirituality where I mean everything is unified.
It's clear you want a simple gauge.
yeah.
Yeah. Well, there could be a hidden sector, but the standard model is simple gauge group. Yep. And I'm just going to say there's some set of axions AI which exists. And at this stage, I'm just ignoring the potential. This is going to be like the cleanest case. We'll talk about a potential in a sec. Then I can just do, I have this coupling. This G is now the field strength of the gut. And I have some sort of set of anomaly coefficients. They could be 0. At least one of them has to be non-zero because I want to solve the strong CP problem. And then I can just do a field redefinition because there's no potential here. This whole sum I'm going to call A over FA. And that's the only thing that couples to gauge bosons. So all I have here is a QCD axion, and all of the other axions are massless and not coupled to the standard model. And so this, I'm going to do this sort of like, and then to derive from this, the standard model couplings, I'm going to do this in a sort of general way, which will help us when we come to the heterotic case. So I can write this trace of G squared, which by the way, I mean, no, sorry, I keep going the wrong way. This trace G joule, I can write it as the sum over the low energy gauge groups after I've broken whatever is in the UV. By whatever mechanism, I start with a gut and then I break to the low energy gauge groups. You can always write it as a sum of the low energy gauge groups with these, what are called embedding levels K. And then non-abelian groups have integer Ks. For the abelian groups, they're rational numbers, which is to do with the hypercharge normalization. But so the simplest sort of case is that if I have some big gut gauge group and it has some SUN subgroup, which is repeated K times, then I break that to the diagonal. The embedding level of this low energy SUN would be K. So if I had 2 copies of SU3 color, 2 SU3s which broke to the diagonal to give you SU3 color, then the embedding level of SU3 color would be 2. So that's one way to, with the diagonal embedding, it's clear to see that these are always integers, but that's a more general result. And for the U1 hypercharge in SU5 or SO10, or the standard gut gauge groups, this embedding level is 5/3. It's a good question. I forget exactly why. I'd have to get back to you on that. I don't have a good answer off the top of my head. there's some sort of like normalization of the minimal charge. That's like where you get these rational numbers from. But yeah. So,
But I was interested.
yeah.
Go back to- see, go back to the top. This sum of all
Yeah.
the axions you imagine.
Just at least one.
Think of like an axios. Is that what you're thinking?
I'm not necessarily, I'm just gonna say, I'm just asking the general question, what are the couplings and the masses that are allowed? And I want to solve the strong CP problem, so there's at least one doing that. And then, but the result is general.
Yeah, but this result comes from the axios, so people think it's all these axions.
But it also works for two, if you want to. Okay.
See, so you're not interested in like the axios limit for you. 2 is enough for you.
Two is enough, but what I want is I'm going to find a bound in the parameter space on that plot, and that bound holds for all as many axions as you like, whether there's one or there's 100. And it just comes from this anomaly coefficient. Okay, so then if I expand my original gauge, the coupling to the gut gauge group with some LA here, then I get exactly this. So this is the couplings to the standard model. So I've called them E and N like we did in the previous case. Plus, there could be other gauge groups here that are not. Sorry, there could be other gauge groups here, which I'm not considering, but at least the gut breaking to the standard model, you get this ratio of E of N is equal to this combination of the embedding levels. Basically, because it's a ratio, this curly A drops out, and then E gets a contribution from hypercharge. So K1 is the hypercharge embedding, K2 is the SU2 weak embedding, and K3 is the SU3 color embedding. So because the electromagnetism is a combination of the hypercharge and the T3 of the SU2 weak, then you get this K1 plus K2 is related to E, and then N is just given by the embedding of QCD. So for the standard embedding, this is what you get from basically all of the 40 guts, the SU5 or SO10. If basically if the standard model comes from an SU5 subgroup of some bigger thing, then you get this. Where K1 is 5/3 and K2 and K3 are both 1, and you get E on N is 8/3. This is the usual sort of gut story, and this is sort of why it comes about. And then we have a very well-defined prediction. So before, for the QCD axion, so this E on N, you don't have the sort of freedom to choose it arbitrarily in the guts. That's because the anomaly coefficients E and N here are related to the gut anomaly coefficient, which is just one number, and these embedding levels, which we've fixed by how we've embedded things into the gut. Okay. So now I can add a potential. So I'm going to consider a model with just 2 axions. So I've coupled them both to QCD, and then I had this mass matrix, which I'm just going to give a mass for A2. And the reason, but the most general thing, the only thing I'm requiring is I solve the strong CP problem. So whatever additional masses I add out here, the matrix has to have a 0 eigenvalue. So I've just considered one simple case of that where I just give a mass for the N2. If there was general masses, that would spoil the strong CP problem. And then I can just ask, what I want to ask is like, what are the couplings to photons and the mass for both of the axions in this case? So I'm going to have a QCD axion in both cases, which gets its mass predominantly from the GG dual, from the same way that a QCD axion did. So in the regime where the M2 is a very small perturbation, then the QCD axion, which I'm calling A, is going to be this linear combination, the guy that's sitting out here. And then the ALP, which is the one that doesn't couple directly to QCD, is going to couple, which I've called B, is going to couple to QCD and therefore QED by mass mixing. So the ratio of the photon coupling of the ALP to the QCD axion is essentially the ratio of their masses squared. Okay. And this QCD axion, the coupling satisfies the QCD axion relation. If I instead have this mass very large, I can effectively integrate out A2. So this is above the QCD scale, or the scale of the QCD axion mass. Then my QCD axion is effectively just A1. And my axion coupling for this B, which is now this ALP, is sort of the same order that I would expect from this coupling here.
So the rule here is U versus diagonalized mass matrix.
Yeah.
So in that case, then it's still possible both of the axion couple to GD dual.
Yes. So in this case, when I get the eigenstates, this first case, I basically have this whole combination which saturates the coupling as a QCD axion, and then I have a very light axion which is coupled very weakly only through this mass suppressed mixing. In this case, basically both of them couple order 1 to QCD and QED, but then I have one of them is very heavy because I've added a large mass.
This is all. So. 3%
Yes. Okay, so yeah, this is just a picture showing this. So if I vary the mass of the ALP by changing M2, I have this regime where you have a very light, and this is the ratio of their couplings when I've set F1 equal to F2. I have this sort of light ALP regime where the mass of the ALP is very small, but then its coupling is suppressed. And then there's a sort of intermediate regime where they both sort of look like QCD axions. And then the heavy ALP regime where you have M2 very large. The coupling is sort of the same as the coupling in the QCD axion, but this guy is heavier. And so what that leads to is this kind of plot. This is the axion parameter space in this 2 axion model. We have a mass here, which I varied. This QCD axion line is so one of the axions is always falling on this line because I've put in by hand that we're solving the strong CP problem, and the other axions populate this region below the QCD axion line. So they're either heavy axions with sort of same couplings of the similar magnitude, or they're light axions with very weak couplings. And the sort of bounds in the plot are just from scanning over different, that put some cutoff on the values of the Fs. And you can make a general argument if you have more axions that this should always be the case. You just have a QCD axion on the QCD axion line, and then everything else is below that. So basically there's this cut in the parameter space where everything above this line is just not populated in unified theories. And so this is interesting because this means that if you were to see something, if one of these experiments saw something over here, you could tell something about physics at sort of very fundamental energy scales. At the gut scale, you could say that an axion out here is just not compatible with unification, at least in this strict sense where I have to be exactly unified.
Straight on the extreme left are just from observations of how far the source and so on. It's the appearance of the signal. You'll never be able to identify that it comes from an axion.
Sure.
So even if you have like a firm statement, it disappears, right? Very much.
That's true. I guess I was more thinking about these haloscopes, the sort of projections. Yeah.
So you gave a very, like at the beginning, you gave a very general definition of an axion, which is like any complex scalar.
Mm-hmm.
I have some random extra complex scaling in addition to the QCD axion. And my other complex scaling comes from some negative image breaking, whatever. I can always imagine 2 Goldstone bosons mixed having kinetic mixing with each other, for example.
Yeah.
The QCD axion can couple to the photon. It can mix with the other axion, the kinetic mixing or some other higher direction.
Mm.
Naively, this would let me get really far enough
I don't think so. So this, I guess, like, sorry, keep going. So I mean, I just showed you this setup. So if
My setup, A2 is not even here. A2 is just, it doesn't even couple to GG law.
that's fine.
Doesn't have to do, nor have to do. That's no couplings.
But I can always diagonalize the kinetic. So you can turn, this is just a model. You can make a general argument if I have a general mass matrix here, that I always get essentially this type of result. And then
The key is the first.
yeah,
So you have a line axiom in your set, but it's coupling to this our sector, the game sector is equal weak, so it's to the right. So that's exactly the case. But you didn't provide actual source for coupling.
basically I can
Because it will go through our center first.
So it's to the right.
Okay, I see.
basically like I can write A here. Like if I didn't have A1 on F, A1 and A2, I just had A on F. I can expand that in terms of mass eigenstates with canonical kinetic terms, however you do that rotation matrix. And then that whatever factor appears there, it's going to affect the photon coupling, and it's going to affect the mass that you get from QCD in the same way. So then you always you fall into one of these categories, basically. Okay. And so this is just, so yeah, a discovery to the left of this line would be incompatible with unification. And so I just wanted to quickly mention the cosmic birefringence. So this was a sort of reported but like not confirmed measurement of the signal, which is basically a rotation in the polarization of light from the CMB. And they reported a measurement with like some fairly large uncertainty, which is sort of order 6 times 10 to the minus 3. The contribution that you would get from a very light axion. So the axion has to evolve cosmologic. The VEV of the axion basically has to change between now and the CMB, which means its mass has to be within the Hubble rate. The Hubble rate at the CMB versus now. So this is a very, very light axions, like many orders of magnitude to the left of the, well, I don't know exactly where it goes off, but like far, far lighter than the QCD axion. And it has to change by a sort of order 1 amount because this prefactor here is already 10 to the minus 3. So the dimensionless axion, which is phi over FA, should change by order 1. So if this experiment was confirmed, this would be some kind of pretty strong hint that there was a very light axion and it has to have a large coupling to photons. So this is one example of something which could tell you, for example, that the standard model is not uniform. Just one such measurement. Okay, so this goes back to Tony's question earlier. There's a sort of other class of theories which I've called gut-like, but are often studied in the same context as unified theories of guts, which are not exactly a simple gauge group in the UV. So they still have many or of the sort of appealing features of guts. They solve some of the standard model problems. So some of them can arise as subgroups of SO10. So the example, I'll go through the flipped example, but you can have analogous results for Paddy-Salam or trinification. So flipped is a SU5 with an extra U1. And then Paddy-Salam is a SU4 with 2 SU2s. And trinification is 3 copies of SU3, which can be embedded into an E6. So all of these could just appear as an intermediate stage of some breaking of a more unified theory, or you could study them as a theory in themselves. If they do come from a fully unified theory, then the previous results apply. But if this is as far as you go, you just get to SU5 cross U1, that's what physics is like at a fundamental scale, then the previous result will not apply. So I'll go through the flips case. So in this case, you basically do have a separate coupling of an axion to the SU5, and then you have a second axion which couples to this U1X, I've called it, or you can, but you don't need to put these axions in. And this second guy, this B, because the U1 electromagnet, also hypercharge comes as a combination of the U1 from the SU5 and this new U1. So this B will couple to electromagnetism and won't get the mass from QCD. So it won't satisfy the previous results. And this is for this specific breaking pattern. So you break to the this group to the standard model by a Higgs, which is in the 10 representation of SU5 and also charged under the U1, which is why the U1 in the low energy group has a combination of both the U1 coming from the SU5 and the extra U1. So in this case, you would have an ALP as in something which is and it can have a large coupling to QED without picking up the mass in the same way. But I guess the question, the properties of axions in this type of theory are sensitive to whether you do the extra step of embedding this SU5 cross U1 into SO10, or if you just say I stop here and that's my theory in the UV. Okay. Okay, so any questions about that before I move on to the heterotic case? Okay, so in the heterotic case, there's sort of a puzzle we wanted to answer is whether it's basically the same. The heterotic string models, at least we're considering the supersymmetric models, but then the anomaly cancellation in the 10D theory restricts the gauge group to be either E8 cross E8 or SO32, which is why you might think, well, they already look pretty unified. So if it's SO32 specifically, then you might expect that the same results just apply straightforwardly. And then if the E8 cross E8, if you put the standard model into one E8, which is what people usually do, then again, you would expect this looks just like a grand unified theory. So the axion coupling should satisfy the same results. However, the models in the IR which come from this typically don't look unified in the same ways that the 4D theories do. So there are different mechanisms which work to break the 10-dimensional gauge group down to the standard model gauge group, which are not Higgsing. So it's orbifolds or adding background gauge fields, which is sometimes called vector bundles, but you only leave a subgroup massless in 4D. And the fermions, depending on how it's broken, come only in the representations of the low energy theory. So they don't necessarily, the massless fermions, that is, they don't necessarily fill out a full E8 multiplet. And you generally get fractionally charged states. So this, when I, so in the 4D guts, the electron charge is the minimal charge for color singlets. You don't get, for example, charge 1/3 objects. But in the string models, you typically do, although they're heavy. And this Eon N, which I said was the related to these embedding levels, it's not 8/3. Because you can show if it is 8/3, then you get a full SU5 at low energies. So in all of these ways, these are different from the unified theories in 4D. So it doesn't look unified from this perspective. But what we'll actually find out is that
So when you break a gauge group not relying on Higgsing, what if you're relying on other things?
Yeah.
Do gauge bosons living in the do they still TMS?
Yeah, from the 4D, they're heavy. So like the massless, the massless gauge bosons will only fill out a standard model gauge group, but it's like the higher KK modes fill out the full E8.
You don't use Higgs.
Yes. So I mean, you can kind of think these Wilson lines are like you're turning on VEVs for the gauge fields themselves. So the Wilson lines are like, well, Wilson lines are sort of like having boundary conditions for the gauge field. So some of them don't have zero modes. And then there's some of the full multiplet of gauge bosons are not massless. So that's one way you can think of it. And the background gauge fields are when the field strength itself is non-zero. So that is kind of like something which is charged in the adjoint of the gauge group, which is breaking it. So there's some similarities to Higgs. You are turning on stuff that's in the gauge group. Okay, and so we're gonna basically show that the axion couplings are related to anomaly coefficients, which you can calculate in the 10D theory. And they do sort of see the full gauge group in 10D. So they do, with the caveat that you can, which I'll talk about a little bit, that you can put things into 2E8s in this case, as opposed to having one gauge group. They will satisfy the constraints. They will, the couplings of the axions will look unified. And just some quick notation, K I'm going to use as the internal manifold. So we have a 10-dimensional theory, and then there's some 6-dimensional manifold, which I'm integrating over. That's I'm going to call K. And then we have flat space, flat 40 directions. And I'll be using this, so these FF tilde couplings that I wrote down, I'm going to call them F's. I think in most places I use F wedge F, but if I use trace F squared, that's what I mean. So I'm just talking about these topological terms. Yes.
Also, two possible questions. So one, are the results going to be sensitive at all to how you stabilize or dismoduli in these constructions?
We're not stabilizing any moduli, so yeah.
You're not stabilizing.
Not doing it. I mean, I don't think people really know how to do that in the heterotic things, but it's
I mean, because naively, I
Um,
some line and it breaks me to something. I could also move it around, right? I have lots of Susie without breaking Susie and get it whatever else. And now, how much do results change? So that's one question. The other question is related exactly to Susie. But I mean, couldn't you also have no Susie on space time, but Susie on the worksheet?
there's like SO16.
Yeah,
Yeah. So we didn't consider that case, but yes, you could. I think it would just fall into the same category as the EA. You still have a SO16 cross SO16. I guess like for the EA cross E8, like you could imagine, like I'll go, yeah, you could put, for example, an extra U1 here, which is your hypercharge, but there are difficulties to do that. And I think that's been studied in the EA, the supersymmetric case. I don't know if people have done similar things for the SO16 case. So if you have more freedom to put things wherever you want in the SO16 case, it's easier to get something with like a very light axiom, which would evade these results. But I don't know that model very well.
So you want suit. It's like suit thing.
well, yes, in 1985, that's what people would have said. So have I.
Yeah, so I'm like, but to your first question, I don't think like any of these braking mechanisms or the moduli stabilization would change this, because what I'll present is just an anomaly matching argument. So you can find the axion shift symmetry in the 10D and then match it. So the ratios of the coupling should not be changed by that. There is, yeah. Okay. So yeah, the 10D, I'll just go quickly just to introduce the field. This is not super important, but basically the 10D bosonic action, we just have a sort of very limited set of ingredients. We have obviously the gravity, Einstein-Hilbert term, there's a dilaton, which is not really going to play a part. And we have this H. So H is the field strength of the two-form B. So this B is going to be important. That's where all of the axions are going to come from. And the gauge invariant two-form is this, first of all, just so dB is like the derivative of B. It gives you the kinetic term. But to make it a gauge invariant thing, you need to add these Chern-Simons form, which means that this D, if I take the derivative of H, I get a divergence. It's non-zero, so it's proportional to trace of F squared minus trace of R squared. So R is the Riemann tensor here, and then F is the gauge group, the field strength of the gauge group in 10D, which could be either this E8 cross E8 or the SO32. And then I have the usual kinetic, this is the kinetic term for the gauge group. And then I have this extra coupling here, which is an interaction of B with this X8, which I haven't specified. But this term is completely fixed by anomaly cancellation in the 10D theory. So this X8 is known as just some complicated function of the Fs, and it depends on which of the gauge groups it is. I haven't written it out, but essentially this coupling here is going to be responsible for some of the axion coupling. So this is just where everything comes from. But essentially what I want to do is find this two form. I'm going to go down from 10 to 4 dimensions, and this two form is going to become a whole bunch of axions. And then I'll find their couplings to the gauge bosons F. That's sort of the name of the game. So it's kind of a more complicated version of the gut story where I just had the axion coupling in 10D at the UV, and then I wanted to match what was happening in the IR. And now I have to keep track of this two form and how it sort of dimensionally reduces into becoming a set of axions. Okay, so I've kind of said a little bit of this already. So the axions come from this two form field B. In the usual notation, it's just a 2-index field. I have what's called the model independent axion, which is the dual of B with its indices in the sort of 4D directions. And then I have the model dependent, these little bi, so I can expand B with its indices in the internal direction, so in the extra 6 dimensions. And I can expand this B in some basis of what are called harmonic two forms, beta, and the expansion coefficients of the axion fields here. So this is so these are model dependent in the sense that they depend on what manifold I have chosen. So different manifolds will have different betas here. They'll have different numbers of 2 cycles. And that will lead to a different number of these model dependent axions. But the model independent axion always is there. Okay.
What state of join can
They do some heterotic axions. They do. Yeah. And the couplings of these low energy axions, I have the A, the model independent, and these BIs, the model dependent, are fixed by anomalies in the 10D theory. That's what we're going to look at. So I'm going to just go through a 5D example first. Oh, geez, I'm running out of time. So if I consider, so in 5D, the axions come from a gauge field in the extra dimension. So that's the analogous thing to the two form B. So the axion in 4D is given by the integral. So I'm considering just an S1, so one extra dimension. And then the axion is the integral of this gauge field A over the extra dimension. And in the 5D theory, the U1 has a shift, one form symmetry, which shifts A by a constant. And then the axion shift symmetry in 4D is just given by integrating this basically. So the axion shifts to A plus whatever this constant is integrated over the S1. So the 5D analog of the axion shift symmetry is this one form symmetry of the gauge theory. And the current of this symmetry is given by this Hodge star of dA. And because I have this Chern-Simons coupling here, this current is not conserved. It has a divergence which is proportional to trace F wedge F. And so to match the anomalies from the 5D to the 4D theory, we sort of do this procedure, which is basically, you can essentially read off the anomaly here. This is going to be the coupling here. It's going to be axion coupled to this. But to do this procedure, you imagine coupling J to a background gauge field, and then you derive this anomaly polynomial, which is given by this divergence, or the divergence of both of these guys. And then I find you can integrate this over the S1 to get the similar anomaly polynomial for the 4D theory. All of this reduces down to giving you this axion coupling here, which I could have just much simpler, just integrate this over the S1 and then I get the axion is just this integrated over the S1. But this is sort of a more complete way of doing it, matching the anomalies.
Somebody argues that 4D eccentric symmetry is stemming from 1D gauge transformation. And
It's not a gauge transformation, it's the one form symmetry.
it's wrong.
Hmm.
And the one way to see that is to look at divergence of the current of the gauge symmetry. And
Mhm.
it's normally free. So that DJ is actually zero, but this isn't it?
This is the current associated with the one form symmetry, not the gauge symmetry.
And that's is it anomalous? This electric symmetry?
Yeah,
How would the D star J, where J is electric symmetry, then just is 4D normal? How do I see that?
well, I mean, you can see it from here. I can just integrate this and then I get a trace F wedge F, right? And that tells me that this shift symmetry, which is a zero form, the usual Pechi-Quinn symmetry, or the continuous version, has an anomaly.
What gauge transformation is portion of the axion shift symmetry in 4D, and
But it's not the gauge transformation.
then one can just tell him divergence of that current of the gauge symmetry is actually zero. Because
Yes.
it's gauge symmetry and normal. Right. So there's no way to reduce the 5D divergence of the current to the 4D divergence of the shift symmetry, which is anomalous.
But this is not a gauge. This is not a gauge.
I agree with you, but
Okay.
somebody argues, shows.
Yeah, that made this one way you can see it, I guess. Yeah. Is that what I said? I get you now. Yeah. Okay. So right. So you can do a similar procedure for the axions coming from the heterotic string. So I said this model independent axion is related. So to B, this sixth form is the dual of the two form B. And I can integrate it over all of the extra dimensions. So this is integrated over the entire manifold K. And then I have some global shift symmetry of this sixth form, which when I integrate everything becomes a global shift symmetry of the axion. And the current here is actually this field strength of B, the two form B, which is also has a divergence. And then I can do this same sort of, that's the wrong way. It also has a divergence, and I can do this sort of anomaly matching procedure again to just find that so I've dropped this trace R squared term in the final line. I find this anomaly polynomial in the 4D theory. So it comes from just integrating the 10D version here. And then I find that the model independent axion couples to this trace F squared, which is the full gauge group. So it couples in a gut symmetric way. Yeah, okay. And then the model independent axions are slightly different. I have to expand these in a basis. So, so I take the two form, I've expanded it in this way. These CIs are the sort of submanifolds of the 6D manifold that I've compactified on. And then I can invert this relation basically by integrating over these CIs. So by this definition, so you can always choose this. And then I have, again, this two form in the 10D has this global shift symmetry. The axion shift symmetries are just given by this global shift symmetry integrated over one of these two cycles. And then the current is again, has this divergence. So this X7, which I haven't been writing out, but this X8, which I wrote in the action, is related to the Green-Schwarz anomaly. And X8 is the derivative of X7. So repeating the same procedure, I'll just go through this quickly. But basically what I end up with doing this anomaly matching procedure is that I get the model dependent axions coupled to, for the E8 case, I couple to the first E8 with a positive sign and the second E8 with a negative sign. So they have a separate coupling to each of the two E8s. That's essentially the main upshot of this whole procedure. And there's an integer coefficient here, n, which is related to, this is an integral over the internal manifold of this harmonic form. So this is tells you where the axion lives in the extra dimension, and it depends on the background values, the vevs of these gauge fields in the extra dimension. And this is some quantized number, it's an integer. So basically I get an integer number and it couples with the opposite sign to each gauge group. Okay, so the upshot of all of this, the anomaly matching is just to show that it's like it's a robust argument. You can match these coefficients from the 10 to the 40 theory, and it doesn't matter about how you break the gauge groups or do things like modular stabilization. Did you have a question?
So is index of beta determine number of axiom?
Yes. So that
Index,
well, it's a property of the manifold. You have a 6-dimensional manifold. It can have any number. It could have 0, but it could have many more sub-manifolds, which 2-dimensional. And the number of those.
I runs from 1 to something.
Yes.
And
that
number of axiom.
exactly. Yeah. So this is, yeah, when people talk about the axiverse, they're usually doing type 2, but it's a similar kind of thing. And they consider very complex manifolds with large numbers of these closed submanifolds, and then they get very large number of axions. But that's what they need to assume to do that. Okay, but then essentially if I just do this whole procedure in the 40 theory, I have 2 linear combinations which couple. So I'm now focusing on the E8 cross E8 case. The SO32 case is just more trivially a gut. But I now have one linear combination of axions which couples to the first E8 and a different one which couples to the second E8. This one is the model independent axion couples the same way to both, and then the model dependent axions couple with opposite sign to both. And in the same way that I expanded the gut gauge group in terms of the low energy gauge groups with these embedding levels, I can do the same thing with each of the E8s. And I have the same embedding level K for each of the gauge groups from the first E8 and then a different one from the second E8. So if in most models, well, essentially all models where people have put the standard model into a heterotic string theory, they've said all of the K2s are 0. They just keep the second E8 as it is, and then put the standard model into the first E8 and have some embedding levels, usually trivial ones. But this is the sort of most general thing. So if, for example, if the QCD K for the first E8 and the second E8 were both non-zero, the QCD would be coming from both gauge groups. Which is the most general thing you can do, but there's some issues with the model building, which I'll go through. But basically the requirement to have an ALP is that this E-on-N ratio, so this is the E-on-N I would have got from the first E8, and this is the one from the second E8. If they're not equal, then the coupling of that, you can have a ALP which is coupled to photons, but not to QCD. If they're equal, and also non-zero. And let's do this.
So when you say sample gauge group is embedded into both E8, does that mean the lower sample gauge group is a diagonal subgroup?
Yes, yeah. So then you hit through the diagonals. Yes. Yeah. Well, that's a good question, actually. So I'm just being very agnostic here. I think so. Actually, for the non-abelian gauge groups, I don't know if that's actually possible. I think there's sort of ingredients in principle there. In most of the literature, essentially has not done this. It just put everything into one E8. And then there's some issues with that, like the massless matter fields are typically only charged on one of the E8s. So you kind of need all of the standard model gauge groups to come from one E8, and then maybe you could also have a contribution from the second E8, then you would have no matter charged under it. So you at least you need the entire standard model to have a contribution from one E8.
I'm sorry, one more question. Like in the case where sample gauge group is embedded into a one of E8s,
yeah,
is it still possible to have, maybe you will explain, is it still possible to have the two formats and coupled to both of E8s?
The axions do couple to both E8. The model independent axion always couples to both E8s with the same sign. Why is it a problem?
It's a quality problem.
Oh yeah, you
I think it will.
yeah, but if you have the model, they have the model dependent axions as well, at least one, then you have a separate linear combination coupling to each.
Combination.
Yeah. So you basically get like,
But didn't you say?
so you get like A plus BI.
Second states instead of just identifying this linear combination sitting in front of the square as a one axiom. Actually, you said what you need to do is a mass matrix.
Huh?
At the very beginning of your talk, you said when I identify axiom,
Yeah,
I cannot just identify A plus B as a one axiom, A minus B as separate second axiom. What I need to do is to mass matrix diagonalization to figure out the mass second base.
that's true. But
then it's still possible to have two axiom, both of axiom coupled, both KG group. That's what you were.
but the I guess the point of the first part was that like our result essentially comes from the fact that the coupling of Q to QED and QCD is the same, and it's independent of the mass matrix. So the diagonalizing, that mixing procedure where I gave you that scatter plot, that didn't change the fact that there was that bound. So actually it doesn't really matter what the mass matrix is. In the gut case, you can only couple to QED and QCD with the same strength. The ratio is this E on N, which is 8/3, and you know it. In this case, if we put, if I just have done what all of the sort of standard model building has done in the past and just put the entire standard model into this, I get this linear combination couples in the exact gut symmetric way. And then there's this other linear combination, which will generally get a very large mass because this will confine at a very high scale. Yeah. This is the sort of general thing that you would need to get an ALP. So you need to embed the standard model in some way, non-trivially, into both. But yeah, this Higgsing to the diagonal procedure, I don't know if it's possible. I haven't looked into it fully because you don't generally get matter fields which are charged under both, and so, or not scalars, so you can't Higgs them. So I don't know if that's actually possible, but at least for the non-abelian gauge groups. So, but there is the one example. So my collaborator Mario with Timo Weigand at Hamburg, they recently had this paper saying that